All right, guys, let's get started. Sorry about that. So we are recording now, I believe. Yeah. So, a couple of things. Let's talk a little bit about the WECA assignments. Okay, we'll start with that. Yeah, and then we're gonna continue. What was the issue? This happened the other day, didn't it? Okay, there it is. Yeah, so today we're going to talk about the WECA assignment. Then we're going to talk about the new assignment. I have a new assignment. This is more of a mini project. So that means it's a little bit longer, but more involved. So I'll talk about that. That's going to be your KNN assignment. You will only have one KNN assignment. And that really gets us into the end of the first third of the semester, right? So at the end of the first third, it's around the first exam, week 6. And then after that, the second third is going to be neural networks. So that we shift gears to another topic. All right. So first thing is, let's take a look at 365 here. So now let's go to content. Pretty sure WECA, right? So this is WECA. And I did provide a deadline for this, but I'm going to extend the deadline on this assignment. So it says due date today, right? I'm going to extend it by 1 week, but that's because we're doing the presentations a week from today. Remember, everyone needs to present their WECA topic. It doesn't need to be like a huge presentation, but you're all getting different data sets, correct? 2 classification and 1 regression. So I think it'll be very useful for you guys to see what your classmates did actually. All right. So if you have any questions, you really need to see me. And everyone needs to present. Your grade will be based on the presentation, right? That you completed the task. Does that make sense, guys? Are there any questions about that? All right. So I'm just extending the deadline here. So it'll stay available until yeah, so it'll stay available until the 10th, right? But everyone needs to present on a week from today on the 1st. Any questions about, okay, there's 2 questions. On all of them, on all 3. It can be quick, right? So you don't have to demo it or anything like that. I really just want to see in your PDF report talk about what the data set was like, X and Y, right? How many samples, how many features, how many classes, that kind of thing. Some idea of what you did, like was it cancer or whatever it was, right? And then performance metrics. Does that make sense? The whole pipeline. Yes, sir. No, I'm not really concerned with the presentation, but the substance of it, that it's correct, right? That's basically what it is. I think it's a good thing for you guys to see, all the presentations. It'll make things click in your head, I believe, because it'll be a whole bunch of different data sets. And you're not distracted by coding or anything like that. You're just doing it in WECA. Got it? So extended by 1 week, but you have to do your presentation. As always, you have to submit a report, right? The PDF report kind of your results as well. Got it? Any questions on that? All right, that's settled then. Now the topic that we're covering that we started Tuesday and we're going to continue next week until the exam, basically exam 1, which will be on week 6, is KNN, right? So KNN is a very nice topic. So it's our first algorithm in machine learning that we're studying, and we're implementing it in Python with NumPy. I'm going over the pipeline basically, and I haven't really gotten into the algorithm itself. We have plenty of time for plenty. All right, so yeah, I'll continue doing that. And then I've already decided what the homework assignment will be for this. So that's what I'm going to talk about today. And I think, yeah, so I haven't added the link yet, of course, anywhere, I think. Right. So this semester, I'm going to do a new homework assignment for this. I will give you basically have until probably week 6. So if we have the exam on Tuesday, then on Thursday is when we would do the homework. Again, you will present this, all right? Just short presentations, but I think it's an idea. I know it works, and I think you guys will like it, but it's challenging, right? So it's a bit challenging. So the idea is, and I'm going to switch to the whiteboard for this. Today, I'll use the whiteboard a lot because we're discussing, the Euclidean distance and things like that. I did prepare some materials for this. So you'll have a lot of material and code. So I provided some code for this. All right, so let me switch over to the whiteboard, right? And to tell you what I want to do, or what I want you guys to do for your homework. So this is the whiteboard. Okay, great. So KNN is a vector space model. I think this exercise actually will help you to really grasp these ideas of vector spaces, okay? Now, I'm sure you guys you listen to the news a lot and you hear a lot about generative models, right? You're always hearing about these models that generate code, generate text, or generate images. What if and you hear that they use AI, that they use deep learning. What if I told you that you can actually create a simple generative model just with KNN, right? So that's what you're going to do, okay? You're going to you're going to use images, and you're going to generate basically images based on input conditions. It might sound very difficult, but it's actually quite straightforward, okay? So what's the idea here? The idea is there's basically 2 parts to this, okay? You're going to need images, and the images, I would like for these images to be unique to everyone, right? You're doing this individually. Also, you can help each other out, of course, and I'll provide a ton of examples of this. But there is quite a bit going on. You're also going to deploy this. So I want you guys to deploy this on GitHub, and it should be a tool that actually works, okay? So now you guys have taken a lot of HTML, CSS, and JavaScript, I'm pretty sure, so you know a lot about that. So you'll leverage some of your knowledge of web development, okay? But I provided the example, so really you just have to read the code that I provide and you'll understand. So the idea is you're going to have a whole bunch of images. Now, one key condition is that the images need to be the same size, okay? So let's say, for example, that they are 250 by 250 pixels. Now, I'm not giving you this data set. I leave it to you to find. But for this to work, right, the images all have to be the same size, okay? This is important. So what I want you to do is I want you to tell me, imagine you have a website, right? The website, looks like that. So let's start with the application, actually. And maybe you have some text boxes, or it could be, what do you call it? A sliding rule, right? You guys know the sliding rule. So it could be something like that, either a sliding rule or text boxes. You will input values in there. And based on those values, you're going to generate an image. You see what I'm saying? So the example that I'll give you is, for instance, a furnace, the Gary US Steel furnace, right? So that furnace looks kind of like that, something pretty big thing, right? And this furnace gets in coal. It gets in things like natural gas and a lot of things, right? So, you got the iron ore, or whatever, that's coal. And then there's the natural gas that comes in. So that's like the physics of what's going on in there. So how would you control that? So you could say, for instance, I'm going to give it 50 tons of iron ore or 1,000 tons of iron ore. You see that? Or you could say over here, I'm going to give it, 0 natural gas or whatever, how many units of natural gas you give it. So effectively, what's going to happen? If you gave it probably more natural gas, what would you expect about the furnace? It would get hotter, right? That's kind of the idea. So then you can imagine that the images that you would have are like infrared. Is that what it's called? Infrared, right? Like when you can see the temperature. So you add more natural gas, it becomes more, like yellow. This is more yellow, for instance. Do you see that? Or you give it less natural gas, even to the exaggerated case of 0, then what is this? This is going to be not as yellow, but greener or something like that. Do you guys understand? Now you have 2 options. You can do this in black and white, which is called grayscale, or you can do this in color. Actually, for this problem, although it might seem like it's difficult, doing it in color shouldn't be a problem. So I strongly recommend that you do it in color. Okay? And believe it or not, you're going to do this with KNN, and that's it, and NumPy, right? So you're going to do this in NumPy, and basically that's the idea. So this is the app that I want you to develop. For this one, you will have to use PyScript, which is, I think I mentioned, is the new, as of 2 years or so, it's a new tag in HTML that allows you to write Python code in HTML, very much as we do JavaScript already. That makes sense. Okay? So your application needs to, as I said, you can choose text boxes. It doesn't have to be 50 text boxes, right? It could be 4 text boxes, whatever you want it to be. Or it could be these, scroll bars. The thing is, you need to change the values and the images need to change. Okay? Does that make sense so far? So that's the application. So then now we're going to talk about the tools that you're going to use to make this happen. First, I'll talk about the algorithms. I don't mean like the actual code, HTML, right? But I just mean the algorithms. So actually, it's very interesting. You're going to have basically a data set of images, right? You can spaghettify these images because you already know how to do that, and you can just create a file, okay? But imagine every sample here is what I'm saying is actually an image, right? And you're going to have associated with that image a vector of some values. Let's say from F1, F2, ... to Fn, whatever that is. And that can be, this F's here are the text boxes or the scroll bars in your web application. Do you guys see that? So actually the KNN, so there's 2 things. There's this, the images, and then there's these feature vectors, okay? So the KNN will only be applied on the feature vectors. We're going to use KNN basically to create a vector space. And in that vector space, we're going to represent every single one of those samples, but only based on these features. Okay? So why do I want to do that? Because these features are going to be descriptors of the images themselves. So for instance, just for the sake of an example, let's imagine that these images are really hot. So I'm going to say like hot of the furnace, right? And these are really cold. So then we don't have to look at the images, right? We can just look at these descriptors over here. Maybe F1 indicates the level of how hot it is, right? So maybe it's going to be like 50, 40, and this one is just like 2. You see that? So that is the information that is going to help us to represent the images in a vector space, okay? And what happens in a vector space is that you can think of all these images. Forget that it's a big image, 250 by 250. They're just points, okay? They're just going to be points in the vector space, okay? So then now imagine we're going to create a vector space which is just a space, like this three-dimensional space, right? So this is a space. I think I did this analogy where all of you have a position in, right? X, Y, and Z. But I also stated that we can have vector spaces of more features, and it works just the same. So you guys know, for instance, this sheet of paper here is a two-dimensional space. I can use this line as a one-dimensional space. This is a one-dimensional, two-dimensional, three-dimensional. Why not four-dimensional? The math holds. And all you have to do in your representation is, when you have just one column here, what is that? What dimensionality is it? R1, it's the pencil. When I have two columns, I'll just do this, two columns, then these two together become R2. What is that? Sheet of paper. Okay, so let's keep going with that analogy. So now I'm gonna, if I have 3, F1, right? That's just a line. F1 and F2. F1 and F2, that's a two-dimensional space of sheet of paper. Okay, we don't need a third dimension. F1, F2, F3. Okay, three-dimensional space. Denoted as R3. What is that space? This volume that we live in, basically. So you have seen that our text files, Iris has an F4, right? You've seen that, has 4 features. What does that mean exactly? It means that although we cannot, it's impossible for humans to imagine this 4th dimensional space, the math is exactly the same as 2-dimensional, 3-dimensional. So imagine effectively that you've added an F4 in here, and that this one is perpendicular to the other dimensions. Okay, mathematically it holds, so that Euclidean distance function that I'm going to give you today does not care if it's 2-dimensional, 3-dimensional, 4-dimensional, 10,000 dimensional, right? You see that? So we said that MNIST, for instance, is 28 by 28, which is 784. So F1, F2, F3, F4, all the way to F784. That space, I'm not going to draw that because that would take me an hour to draw 784 axes, but basically that's why you write 784. And the math holds. Regardless, what the important thing is, this row, whether you have F1, F2, F3, F4, F10, F20, F784, all of these exist in a vector space, and they are basically points. One point in that vector space. Do you guys see that? Does that idea? It's really important that you get this concept. Okay, this is the vector space model. It's like an extremely important way of representing your data, and you can do, you know, a machine learning algorithm like KNN with this idea. I will retouch on this and I'll try to give you more examples, but are there any questions at this point about this concept? Nope. All right. So then what are you guys doing for your homework? So I think your homework will be fun. And I'll tell you one idea that I was thinking about. I haven't really thought about it exactly, but I think it's possible. So now the question is, as I said, you're going to pick images. You can pick any image that you want. I do have one example I'll provide, which is of these US Steel pictures, okay? But basically, the images, you know, they have to, this is one really important thing. They have to be the exact same dimension. So let's say 250 by 250. Okay. Now, the vector space will not be created based on the images, okay? Instead, think of each image as just having the file name. So you're going to have, this is file 1, file 2. Okay, you have to keep track of the name of the file in the vector that you're using, like you would with the class. Okay, so then the vector space is actually going to be made of the features that you select for your image, and you can create those. It doesn't. This will work with small, a small set of images. Fn. okay? So then you need to have everything, you know, let's say you select n equal 15, okay? What does that mean? It means that every sample needs to have these 15 features consistent, right? No missing data, like in the furnace. That means that your space dot, right? So it's got F1, F2, F3, and then let's just say F15, dot. So there's all of these, but they are perpendicular to each other, which here, these are called actually orthogonal. That's the term, because it's in higher space, okay? So the key is, remember, every image in here, if it's a space of F15, is basically what? A point in there. Does that make sense? It's a point in there. So what's going to happen is, as I said, let's say that you have some images where the furnace looks hotter. They put in more natural gas, more coal, whatever makes it really hot, right? Those images look very yellow, I would assume, right? And because it's in color, it shows that the heat is really high. And then you have other images where the furnace is kind of cooler, so they look darker green or something such as that. So let's think of in an exaggerated case how that would look. So some points would cluster around this part of the space. And then other samples or images, which are points, would cluster around this side of the space. Why? Because these features, F2 and F3, are basically really high. Do you see that? So it puts the values of F1 and F2 in a really high position. Do you guys see that? Whereas the cold ones, actually, if this is F15 over here, right? Or actually, let's look at F1 and F15. So it's basically like a little bit lower. This is somewhere in the middle. So that means that F1 would be maybe, for the cold ones, 20, 10. And for the F15 would be somewhere, I don't want to write over this, but imagine somewhere in the middle of 0 to 100. Do you see that? So effectively, the points in a vector space move based on these values here. Do you guys see that? So the hotter ones for F1 and F2, notice they're clustering around here. Okay, so they're clustering around here, the hotter ones. And then the colder ones are starting to cluster around here. Do you guys see that? Does this make sense, guys? Yeah, please, go ahead.
What did you say the points were?
The points are vectors. So these vectors, right, of F1, F2, F3, all the way to F15, define essentially a space that is of orthogonal, or 15 orthogonal axes of R15. Just like R3, we have 3 dimensions. We just add a 4th column, 4-dimensional. A 5th column, 5th dimension. That's it. That's all we have to do. And every single one of these vectors or rows are a point. Okay, in this vector space. Between what? Well, it can, but in this problem, what I want you guys to do is to basically say, you're going to generate new images, right? And we're just going to do a nice little trick. You're going to use KNN, right, to say, well, I want to produce a furnace image with these conditions. Okay, what does that mean? You're going to go in and create a new input into this space where all those inputs are already there, right? And you're going to say, for whatever reason, I want my F1 to be 37. I want my F2 to be 43, and so on, ... What does that mean? Effectively, let me change color again. So this dark green could be, for instance, that one there. That's where it falls because of those measurements. So then just by putting in the inputs as you put them, you can now generate an image similar to the images around it. Do you see what I'm saying? And how does that work? KNN just takes the distance, looks at the closest, let's say 10 or 5. So it's going to take these closest to it, and it's going to produce an image that looks like those images. Do you guys understand? That's what you have to do for your problem. Now, notice that this feature space is just for finding the closest points. Once you find the closest points, what you should return is the file name of the 10. Let's say you choose k equal 10. So you're going to choose the 10 closest points to the point that you inserted in there, right? What you do really is return the names of the 10 closest points, the names of the file. And once you have these 10 files, because they're all the same size, you can simply do what? An average. A pixel-based average that will render an image that meets the conditions that you set about. And essentially, that image didn't exist because maybe you never had these values in there, right? You had values maybe up or down, but now by just taking a simple average, you have rendered an entirely new image. It's a generative model in that sense. So this part is actually super easy because you guys know with NumPy how to take 10 images and average them out. They're all 250 by 250, and you produce a new 250 by 250 image that is the average of all of those. The key thing is how do you select the images, right? And selecting them requires you to use KNN. KNN usually gives you a class. In this case, it's not going to give you a class. It's going to give you the file name associated with that vector that represents that image. And then by having the 10, you just average. And you can do a lot of things that are fun with this. I even thought I was thinking about this, like, would it be possible to make a person look like a cat, more like a cat? So I haven't really thought it out, but if you think, I'm going to use the three-dimensional space, okay, because it's more intuitive. But keep in mind, it's just a larger space. So if I have, let's say, pictures of cats, right? So all of these are cat pictures, right? You have a whole bunch of different cats, actually, not the same one. And then over here, you have, like, I don't know, something else, right? An alligator. Now, there's conditions here, like it has to be in front, right? You know, it's not so perfect that it's gonna like figure out how to do different. So it's gotta be, you know, but if you introduce the person in there with characteristics, you know, that make it closer to a dog, you could change the algorithm, right? Then you would, what would you do if these are the closest images? You would eventually produce an image that is the average of what's there in the neighborhood. So the trick might be that you'd have to insert the same image a few times, and then it would average all of these. So it might render a person with ears or something. And then you can start to at least get a sense of how these generative models do these tricks where you say a person, but it's a cat on the moon with, you know, whatever. You can take it as far as you want. At the end of the day, just do your best. Do you guys understand? Questions? I think I showed you this at the beginning of the semester when I was doing the demos. I want to say.
The final projects out last.
Yes, when I was doing the final projects of previous semesters, I think I had that. So I'm trying to, so let me see. I'll definitely provide everything that you need, except the images. I'm not providing the images, and you need to figure out the vector representation that you're going to use. So you need to really understand KNN. You see that? That's the whole trick. Everything, all the code is provided except for that initial representation of the vector space, and you do need to get images. So where was the first class? Was this one?
When you say question.
Yeah, please go ahead.
Say images like would it be, for example, picture of a bird, right?
Yep.
One species, specific species of a bird, same picture, like same, or like different pictures of the same species. You know, like a clear picture of like maybe 100 different pictures of like, of a crow, right? But they're different pictures of the crow, but they're a crow, if that makes sense.
Yeah, that will work, but make sure it's
Right,
from
like
the
it's
front.
clear, it's a clear
It should be
picture.
always the same position, for
I see,
instance,
okay.
because you want to render like a passport picture, right? You guys, passport picture. So that way that you have a passport picture, let's say that's your input into this space that has cats, dogs, and whatever. So as you play with the parameters, this is probably how it would work. You would play with the parameters of your face, and so you would move it effectively in this vector space closer to dogs or cats or whatever, take the average of that, and then possibly put ears on a person, because it would average that into the produced generative image. And it's very simple. It's just KNN. Do you guys understand? Questions? I think actually where I had this was in the links, the resources. I want to say I put this in the GitHub, maybe. Did I put it there?
With the examples of the projects of the.
Are they in the
I think so, I don't know.
Okay. Okay.
But I think that's what I.
Because I want to show you guys. No, they're not here. Don't remember where they were. I thought they were on, Go to the GitHub. Deploy to web, maybe. Here they are. Okay, yeah. All right, so these are, yeah, it's this one. So this is literally the application that you guys have to build. So it's like, you can just take this code, it's all there in the repo, and build it. So this has HTML, which I think you guys know how to use. It's got JavaScript, which I think you guys know how to use, CSS, all of that you already know how to do. And then it uses PyScript, right? And in PyScript, you can actually write the Python NumPy code in there to do all the functionality. And the images should be there. It's taking a bit. So it's, yeah, but it usually loads. Yeah, there it is. Okay. So as you can see, what I'm saying is, let me move all this stuff. So this is your project, guys. Okay. Now I wrote a lot of notes for this, so I'll provide that link to you guys soon. How do you move this? Anyway, so here I have some text boxes, right? So I change the value there, right? What does that represent? There's 10 text boxes, so that's 10. So what space is this? R10, right? It's a vector space of size R10, because every one of these values represents a feature. You guys understand? Question? Okay, perfect. And now you can change these values, and when you hit generate, boom, there it is. See that? That's a rendered image based on these inputs, because all it's doing is it took all these values, went into the vector space, positioned those values, right? And then it looked for the closest 10 or whatever images and averaged them and generated a new one that never existed before. Okay, so here's another, I don't remember the values, but like if I put 0 here, 0 there, 0 there, I'm just looking that it's a different image, okay? So I'm going to hit generate, and the code just generates another one at the bottom. So I think, are they different? Like this part is very light here, right? And this part is darker here. Do you guys see that? So this is more subtle, but this is actually a project of US Steel, and all their images look almost the same, right? So you guys can produce, as I said, other images. Don't use these. The way that it works is actually these images are just NumPy arrays, and then I use matplotlib to take a NumPy array and create that figure. So all that is in there. Do you guys understand? Do you have a question? So I will provide a set of links, okay, to get to here, the actual repo behind it, because this is just GitHub pages. So I'll provide that. Yeah, please.
Does the repo have the code for the JavaScript? You said it has the code, but can you just Python or has the JavaScript?
Oh, it's got everything.
Oh.
It's got everything. So you can literally probably use this one, because remember that the NumPy code is running here in the background. So we could probably find this. This would be, yeah, this is in I'll provide this link later, right? But basically, so what does it say? Remind me, experiments 2023 July. Okay. It's gonna be here. It's in the repo here. Here. July, and then this thing called GANs. These are not actual GANs. PyScript examples. So it's example 3. Then you would go here. Yeah, example 3. So this should be it. Okay, this is what you guys are. Feel free to use this. Okay, I'm totally fine, right? Use it, but at the end of the day, you're using your own data. And so you're gonna really have to understand, you know, the images and the feature vectors. Okay, so basically here, the CSVs are, as you might imagine, the data, right? And then you have the index, basically. I think I must have just added everything in there. So if you look at index HTML, right, this is, you guys know web development. So it's normal HTML, normal the head section. Notice that in the head section, you start to import something called PyScript, okay? So as I said, PyScript is just like JavaScript, but for running Python code, right? So there's gonna be now a script, PyScript tag in there. Any questions? Yeah, please.
So is JavaScript then a content, or is that through like Visual Studio?
What is?
Like HTML or JavaScript?
I just write stuff in text files.
Oh.
So this is just like Notepad. I mean,
Yeah, I never.
don't worry, I'll provide all. I'm discussing it now, actually. So because I thought about this, I think this is a good way for you to really understand KNN, right? So if I just give you the example, but now you have to do it, right? So it would be a fun project, I think. All right, so anyway, so I'm showing you here, right? You got your PyScript here. Then some of this is just normal HTML. This is the text boxes, right? So in there, the input, so you'll have to create that. So a table. There's PyScript, bringing in some libraries. Any of those look familiar? Matplotlib, right? So you're leveraging what you already know of Matplotlib, pandas, etc. You will have to import this, maybe some plugins from the PyScript project, okay? And then notice here it is. So that's the PyScript tag. And then now you can just start coding in Python. Okay, and this is all on HTML. No need for Visual Studio or anything like that. notice here that I just provided the URLs for the data. And so you can just literally host them on GitHub as well. Your own data can be hosted there, and then you can just download. Okay, so images, I know you guys think of images probably as a physical thing that you have in a file system, but you know now that they can just be grids. So then you can just have the data, because at the end of the day, the image would become NumPy arrays, right? So you can just store them that way. You don't need to have a whole bunch of images. You can create a CSV of the images, okay? The only limit with, you'll host this on GitHub, and the only limit with that is that GitHub only allows files no bigger than 25 megabytes. So that's the only thing. So if you have a lot of images and your file is bigger than 25, you'll have to break it up into multiple files less than 25 and read it in that way. That might be the only, but I don't think you guys will have that many images anyway. So here's basically the code. As you can see, PD read CSV. So the same ideas. You'll read in the files in there, convert them into NumPy arrays. You see that? Do you see that Euclidean distance here? That we're gonna see that. I'm gonna do all of this in Jupyter Notebook actually, but it's the exact same thing because you can just write it in okay. So anyway, so I'm showing you how to read the files. You got it there. I'm showing you how to this is this part, that what is called the Euclidean distance, and this part here, this is the KNN algorithm with the modification that I made, that instead of labels, I have file names. And then once I find the closest file names, boom, I can just retrieve those file names. They're all the same, so do a pixel-based averaging, and effectively you have a generative model. You know, you don't need like fancy stable diffusion or ChatGPT or something like that. You know, KNN can also be a generative model, right? You'll generate images that never existed before. So it's up to your creativity, you know, of how you do it, but this will be the code. You can see here I have, there will be some code necessary to like send the NumPy stuff to HTML, right? So you will need to render things in HTML. So all the code is there for that, you know, my gen function and everything else. That's it. As you can see, it's not even that long of a code. Do you guys understand? So this code you can use either text inputs or scroll bars is fine. But the key thing is you need to get your images, and probably even harder, the vector space. What are going to be the conditions that you're going to use? So you have to use a little bit of your creativity. Does that make sense? Are there any questions? All right, so yeah, that's it. So this is the code, right? So I'll provide the link in the, when I do the homework description. Go back here. And then some of these are files for the data. Images NP. Okay, so that's a big one. See, this is the conditions, basically. The conditions data and the file name is, oh, that's the file name actually with the conditions. Okay. So this is, so in the name, I had the conditions. That's actually a good solution because, you know what I mean? You have the name .jpg, and you can also have the conditions in there. So there's a couple of ways of doing that. Okay. There's another one. This is another representation. Okay, and the ID needs to match the file. So for instance, in this case, if the ID is 5, let's say, and these are the conditions, right? So then in the vector space, you know, this is what is this? These 9 features, right? That's going to be a vector space of R9, right? And that's one point, right? A point in that space. All right, so then you look at other points close to it. Let's say that you selected 4, 5, and 6. So now you need to look 4, 5, the images corresponding to 4, 5, and 6. They're all the same size. Average them, generate an image. Got it? That's it. Okay. The other thing I will provide is something that I've been preparing. And this, I'll provide the link for this. So just go here. So I provided this online. You can just read through it, but it's got all the details on how to create your GitHub account and then how to set up something called pages. So I don't know if you guys know, but you can deploy websites on GitHub. I don't know how many of you knew that. So if you ever wanted to create your own website, you can just go to GitHub and do it there on pages. So this is what we will be using all semester, right? So currently for this first third of the class KNN, we will be deploying with PyScript because something like KNN implemented in NumPy and pure Scratch requires PyScript, okay? But for other things, when we start looking at PyTorch models or something like that, we're going to deploy them with something else called Onyx. But at the end of the day, we will always deploy these things on a website somehow. TensorFlow has something called TensorFlow.js, right? So every semester, I think last semester we used a lot of TensorFlow.js. This semester I may try some PyTorch, Onyx. And so the first thing you need to do is you'll follow these instructions to create your GitHub, your repo, your GitHub, and configure your repo for pages, and then basically deploy your first, what do you call it? Your first website, basically, okay? So once you do that, and there's the code, so you can reference the code. Once you do that, then I would suggest, and I'll come back to this in a sec. I would suggest you try out some of these exercises. So some of these exercises are just simple NumPy examples in PyScript, just so that you get a feel for how it works. And then after that, the third approach is to implement KNN. I got some problems in there that you can try out. And then all of these are the links to the corresponding deployments. And then I'll come back to that graph too. And then this is the actual KNN implementation in PyScript on the web. All right, so that's as far as this tutorial goes. But this is the output that you should get. This uses Iris, which is what I'm using, right? So here the example is you give it x1, x2, x3, x4, right? 4 features, right? And it uses KNN to do what? To give me the class that it belongs. So Setosa, Virginica, Versicolor. What I provided here is a list of test set samples. So basically you can try this one, 6, 3.4, 4.5, 1.6, and it should give you the class. And then you know you did it right. Does that make sense? So I provided the 4 features and the class that it's supposed to predict. Okay? So if you do all of this, then you know how to deploy KNN on here. Then you have to look at the other one, the US Steel one, to do your application. And you can do it like that, but you can't use the US Steel images. I mean, you can do it maybe just to kind of understand how it worked, but you will need to use your own images and you will need to figure out how to do your vector space representation. That I leave to you. Remember that the images themselves are not in the vector space, right? All you need is the IDs or the file of the images. What you have in the vector space is whatever you decide your vector to be. Got it? So let's think of let's do a simple example, right? So I have an example of balls in there, like sports, but let's do an example of cars, maybe. I'm only going to use 3 dimensions, right? So what are 3 characteristics of a car? Give me 3 that are numerical, that differentiate them really well. miles per gallon, right? So 18 miles per gallon versus nowadays like 40, 42 miles per gallon, right? That's one feature. What other feature? What do you guys think? What, just weight of the car, right? Yeah, exactly. So 2,000 pounds, 2 tons versus 4 tons. Does that sound right? Okay. And then one more, so that we have 3. Horsepower, what would it be?
What, maybe like
200?
versus like 500.
Okay, 200 to 500. Okay. All right. Great. That's what you decided. So that's 3 features. We can picture it here. Let's imagine in this vector space. Well, actually, let me use the whiteboard, right? So probably should be using the whiteboard. So this is, as I said, extremely important that you understand this concept. In machine learning, this is definitely a critical concept to understand. But I think this is a good example. So we have the cars. We have 3 features, right? So your data effectively looks like something like that. F1, F2, F3. We said this was horsepower. We said this was weight. And what was the first one? Miles per gallon, MPG, right? MPG. Okay, perfect. So then, what do we have here? Pictures of the cars, but they're not part of this data set. So let's just call it file 1, file 2, file 3. They're literally just an ID or the name that would take us to a picture that could be 250 by 250, 300 by 300, whatever. We just care about the name of the file. I'll even say .jpg. .jpg. This will take the place of the class that we will learn about when we do the proper KNN algorithm for machine learning. Now I do need some reference for the cars, right? So let's say over here, fn.jpg. So we have miles per gallon, weight, and horsepower. So horsepower makes me think of like a Camaro or something like that, right? What's a Dodge, or a Camaro? Camaro, right? So that probably would be in the 400 range. How much do you think that weighs, roughly? Camaro, yeah, I don't know. 38. Oh, so it's heavy then. It's on the heavy side. 3,800. And then miles per gallon, probably not great, right? So 30 miles.
No, they're like 7.
Okay, 17.
They're really low.
Really low. Okay. All right, good. All right. Now let's go on the other exaggerated side. What's a very efficient in all kinds?
So is it supposed to be in scale like the least to?
No scale,
No scale,
just
to be right. Okay.
just the first column always for all samples needs to be miles per gallon. The second column always needs to be weight. The third one. So because you're comparing, for column 3, you're looking for the differences among samples. That's the most important thing, okay? But I need an example now of a car that's the opposite of a Camaro, like very fuel efficient, light, a Prius. Okay, so Prius. Okay, so what is the MPG of a Prius? 40. Okay, 40. What's the weight of it, roughly? 2,800. Okay, 2,800. And what is the horsepower of a Prius? Okay, 80. Let's just say it is fine. You guys start to get the picture, right? So now let's add 2 more for this. One similar to the Camaro and one similar to the Prius. So let's go to the top for the similar to the Camaro. What would be another similar to a Camaro? What's another type of a Corvette? Okay, Corvette. All right, what's the horsepower on a Corvette? 450 more, maybe? 455. Okay, I like that. What's the weight of it? Probably
35 tons.
3,500. Okay, 35. And what is the miles per gallon here? 19. How about that? Okay, great. And now let's do one more so that we have, and imagine we would have more of these, right? But we're gonna do one more example of a car that's now similar to the Prius. Like, wait, which one? Chevy Volt, okay, Chevy Volt. Okay, what is the horsepower? 100, okay, I like that. What is the weight of it? 3,000, okay, good. And what is, 3,000. And what is the miles per gallon? 42, 45, okay, perfect. We got it. This is what we need, right? So now, what is a vector space? It's just every one of these is an axis. Every column is an axis, and they are, we know in school, right, that when we create a space, they need to be perpendicular. This means 90 degrees, right? We can create stuff like this. We know that we add the third one, that's 90 degrees. That property, as we start adding more than 3 dimensions, instead of calling it perpendicular or 90 degrees, it's called orthogonal. But it's the exact same idea, mathematically speaking. That's all we need to know, is that this holds, so that the Euclidean distance calculation that we will learn about in a sec also holds, okay? So now I just drew this for reference, but I'm going to erase it. And now what I'm going to do is I'm going to create the vector space that corresponds to this. So you get an intuition of how this works, and it's very simple. So I'm going to do, right, like that and like that. So I'm going to say that this is going to be F1, F2, and F3, okay? It would be easier for me to do 2 dimensions, much easier to visualize, but let's try this. Switch to red. So the Corvette is going to be, let's think. F1 means, all right, so this is going to be C, P, V, M, okay? Just so that I can represent them as points with a letter in this space. So I'm going to do the Corvette first. So now we would want these to be normalized. So if you notice, this is 17 and this is almost 4,000. So then these axes would be like one would be very long, one very short, right? So what you're doing is normalize them. So, you look at the lowest and the highest and then create, map them from 0 to 1. Okay? But from 0 to 1 is how we will end up doing this. But for now, let's not do that part, okay? So let's just imagine. So let's look at F1. For the Corvette, it goes 19, 40, 45, 17. So I'm going to say from 0 to 50, okay, for F1. So then, from 0, so I need to write that down. 0 to 50. So the Corvette would fall at 19, correct? So that's possibly around here, right? Then I need to look at F2. This one goes 2,100. So let's do it from 0 to 4,000, okay? From 0 to 4,000. Okay, so the Corvette is at 3,500, so that's probably around there, right? So already for the Corvette, it's starting to look like there. And then the last one is 455. So this goes from 0 to about 500, right? And this is 455, so it's somewhere around there. You see that? So then this, you have to kind of use your imagination, right? It comes out to there. Does that make sense, guys? That's the Corvette. It's just a point in this vector space. Okay, now this could have been 2 dimensions, would have been easier for me to draw, but it could also be 4 dimensions and I would not be able to draw it. It's impossible, literally impossible, but the math holds. So you have to kind of like imagine it in your head. Okay, all right, so now let's do another one. Let's do the Camaro, which is similar. So it's 17 about there, right? I'm gonna change to another color. Blue. It's going to be, so the Camaro 17, F2 is 3,800, about, it's higher, right? So a little bit about there. Do you guys see that? So literally about there. Do you see that? And then the F3 for the Camaro is 400. For the Corvette was 455. So it's like a little bit down here. So then this one comes out to about there. That's M. Do you see that? Those 2 points is where they exist in the vector space. And if you notice, they're close to each other. Why? Because they have similar horsepower, similar miles per gallon, similar weight. Now let's look at the other cars that are actually more dissimilar. Okay, so I'm going to switch to yet another color. I use this one. Okay. So this is going to, let's start with the Prius P. So the Prius has for F1 40. Okay, so that's already up here, right? So you can see it starts to do something. The Prius then, if we look at F2, is at 2,800. So, and that goes to 4,000. So that's definitely lower, like about here, correct? You guys agree? All right, so then we go up here. Well, I shouldn't have written that there, but imagine that's where they meet, but that's not the final point. And then the Prius has 80 for the F3. So this is F3, which goes from 0 to 500, right? So 80 would be probably around here. Would you agree? So then that goes to here. You have to imagine, use your imagination, right? But somewhere around there, probably. Did I do that right? That make sense? Any thoughts, questions, comments? So do you see that these two, the distance between these two is shorter than the distance to this one over here, right? Now let's do the last one, which is the Chevy Volt, right? That was the other one that's similar to it. So the Chevy Volt is V. Let's change colors. Browning. Okay, so now the Chevy Volt F1, once again, 45. It's actually a little bit higher than the Prius, I think. Then 3,000, that's about there, so it's similar, right? Let's say about there. So then it comes out that that's where they're meeting. And then 100, probably about there. So if you think about it, you can almost trace it in a similar path there. That's your 4 points represented in the space that is R3, because we only have 3 features. Now, although we can't draw it, you could add F4, F5, F6, and it's the same idea. It would all work. Okay? Just by adding a column, you can make R4. Iris would be represented in a space such as this, and that's why we will be able to compute KNN on it. So now the question I'm going to give you, let's say that I had a new car, and it's more like the Prius and the Chevy Volt, right? So that would be like a Tesla, right? I assume a Tesla. That's an electric, right? So the Tesla then would have similar characteristics to these 3. So it might be like 42, 2,900, 90. Do you see that? So it kind of falls in between them, actually. So then if I take in yellow, so that's going to be the Tesla. It would possibly fall right there. I'm just kind of calculating. What is KNN then? Look at the closest 5. In this case, there's only 5 points. So let's say the closest 3. So it's going to do what? KNN would take the distance. It's called a lazy algorithm because it's not trained. It really just, this is the new one, and it's going to compare itself to all the other points in this space. So it's going to calculate a distance between, so remember, yellow is the new sample, right? So I'm going to use orange here. So you need to calculate the distance between the yellow and that, the distance between the yellow and that, the distance between the yellow and that, and the distance between the yellow and that. That's going to give you 4 distances. Then what do? You sort them from shortest to longest, and you pick the top K, whatever they are. When we do iris, we're going to have 120 samples to play with, right? But that's it. That's KNN right there. This is an algorithm you can implement in less than 10 lines of code in NumPy, which is what we're going to implement in the Jupyter in a sec, and then you guys will implement this for your homework assignment. So remember, you need to define that. For instance, this was a good example, I thought, of the cars. So what would you do? You would need pictures of cars, but they all need to be like in the same, either the side or the front, right? So that, because you're trying to render new images. So always think of the example of a passport picture, for instance. So if you had then, just an example of this, a Corvette, I'm just going to say that all cars that, Corvette looks like that. A Prius is more boxy. A Chevy Volt is more boxy. And the Camaro also, like a sports car like that, something, right? They're all on the side, basically. They all have 4 wheels. So if you introduce these metrics for the Tesla, when you render an image, that image would look more like these 2 cars, right? Than these 2 cars. You would actually take the average of these 2 to produce a new car. You see that? That's it. That's the idea. But remember that the images are not part of this space. The images are just, once you figure out which points are the closest, what are you going to do? Here in this example, to complete it, what would you do? If you're going to pick 2, well, the 2 closest to it are this and this. So we need F2 JPG and F3 JPG. That now are the images that you're going to average out. Okay, so remember, this doesn't work for everything. This will work, especially because you guys don't have a million pictures, right? So if you had a million pictures, maybe. But so, you have to keep it like passport photos. Like an example of this could be family. Like you have your mom's side of the family, your dad's side of the family. You want to see which side you look more like, for instance. That's something you could try. Things like that. I leave to your creativity. Okay. All right. So hopefully that made sense. Are there any questions about vector spaces and how they work? Pretty easy, right? All right, great. So I had some example, another drawing that I did of these balls, I think. So it's kind of the same idea. Sports, I think. There. So this is an example. It's similar idea. You have something like, only I've drawn the balls here, right? So there's soccer balls, there's basketballs, there's like footballs, there's baseballs. If you look, these are supposed to be baseballs. This is a tennis ball. If you look at the closest balls to it, notice that this is like a baseball, but it's green. Why? Because it's both close to a baseball and close to a tennis ball. So it came out as a green baseball. Why did I make it a green baseball and not a white tennis ball? Because there's 3. I'm doing KNN, right? So there's 3 baseballs and 1 tennis ball. This is the target. So basically the average of these four is more on, it's got more baseball than tennis. So it looks more like a baseball, but it's green. It's just an example. I don't know exactly what it would look like, but hopefully this gives you a sense of what I'm going with. Maybe actually balls would be, simple things like that, right? Something from sports, etc., could be a good thing to do. If you're into fashion, tennis shoes, right? All tennis shoes have a basic profile and you can get a lot of tennis shoes. So you want to generate a new tennis shoe that didn't exist before. Or fashion, right? If you're into fashion or glasses, that it might work better for something like that. Where things that have common shapes with a few little changes to the design. And cars actually might, also work. Yep. So anyway, that's the project. Are there any questions? So all the code is provided. I'll provide the links and I'll set the date of it. For now, I'm setting it for week 6, the Thursday after the exam, or possibly a week after. And that's it. All right. Any questions on this? This is kind of the ideas. And now what's left for today is just to start going back into the Jupyter notebook to continue coding, the machine learning pipeline and then KNN. Yes, please, Mark.
So if there's 6 to 5 closest balls, yeah.
In this example, yes. In this example.
Why didn't it like try averaging out football?
What?
Why didn't it try like averaging out the football?
Because it's KNN. Oh, okay. I think I understand your question. Yeah, you calculate the distance. So this is the new test sample, right? You will compare the distance to all the balls, to all of them. You sort them, and then you only pick the top K. So in this example, the top K was 4 for me. And so 1, 2, 3, 4, although the football was close to it, was probably at the cutoff. So it was not included. That's why it's called KNN. You pick the top K. Otherwise, it would just be called NN, and you would use everything. You see that? Yeah. Yeah.
So it's gonna put you towards the 5 nearest observations, right?
Yeah. In this case, it's looking for the 5 nearest. Yeah. Or 4 nearest. 4 nearest.
That's why it's a combination between baseball and tennis.
Yeah. This is meant to be a tennis ball, and these are 3 baseballs.
So it's a green baseball because it's like, oh, it's close to the next one.
Exactly. That's what I'm saying. So the space, the samples of the train set, if you will, does not include this ball. The train set is everything else except this one. The test set is exactly this one. And I'm using this idea of the generative model, right? So I want to generate a new ball. Well, if my K had been 6, this ball would have needed to have some brown and would have needed to be a little bit more elongated, possible, in theory. But because I made it K equal 4, okay, then it's just the average of the 3 baseballs and the 1 tennis ball. So the shape of it looks more like a baseball, but it's green. If you notice, this is a darker green than this green. So it's a lighter green because the white made it lighter. You see, so that's kind of what I'm saying you guys can try to do. You could try to do something simple like this, like objects, maybe material things, like imagine you're trying to create a new fashion company where you want to design purses or something like that. So you have some purses and then you move them. What would this purse look like? I'm going to put some leather into this, something like that. Any other questions? Yeah, please.
You actually need to find.
You need to find the images. Yeah, so I drew these. I don't know that drawing will work so great. I haven't even thought about it. Maybe, I don't know. Color is definitely something I recommend that you have in there because color will be the most obvious thing that gets averaged. So that you'd be able to see results, whereas, and start with something simple. Like I think like things, articles, clothing, well, mechanical things that have similar shapes, laptops that all kind of have the same shape might be a good approach. And that definitely the images do need to be all the same size in terms of pixels, but they can be big though. You're just limited by what GitHub will limit you of 25 megabytes per file. Anything else? All right, so that's the project, as I said, and you can start working through it. Pretty much use the US Steel example that I provided. This one just renders the pictures down because I wanted to see the differences, but you know, you can do however you want. And everything is in there. But yeah, you need the images and then you need the file descriptors, what they're going to be. And you may need to do that manually. It's possible that you need to, if you did something like shoes, right? You would create a vector of size 10 and you would say things about that shoe, like this is more sporty, this is more formal, this is more this material or that, you know. You have to think. I honestly don't know, but that's the part that you really have to think about. All right, so if there are no more questions, we have a few minutes left. So let's just get back to the Anaconda code, okay? And get to that. Or actually, you know what? Since let's do the Euclidean distance, actually. Let's do that, and then we'll do the code on Thursday. So you guys probably remember the Euclidean distance, but I will discuss it. I do have that picture of this guy in here. Do you know who that is? Do you remember this from high school? That's actually what we're using. Do you remember this this definition? The theorem by Pythagoras? Right? Yeah. Well, that's exactly what we're doing. Okay, so we have basically the theorem states that a given triangle, that given a triangle, the sum of the areas of the two squares of the legs A and B in green equals the area of the square on the hypotenuse C in green. So that's this idea, right? Right there. And that's really exactly what the Euclidean distance is, right? Because we can take that here now. I'm going to do this for 2 dimensions, right? So we have 2 points, S1 and S2 in this space, right? S1 is made up of Q1 and P1. S1 is Q1 and P1. You see that? Remember that this applies whether it's 2 dimensions, 3 dimensions, 4 dimensions. Okay, and then I have S2 over here. So S2 is P2, Q2. Do you see that? So now, based on Pythagoras theorem, this one over here, basically you know that it's C2 equals C squared equals A squared plus B squared, right? You learned that in high school. And that's exactly what you use in vector space models. So then that just becomes this. We know that we want to be able to perform this calculation, right, of A and B. So what is A and B? A is this line, B is this line. You see that? And how do you get at A and B? Well, you know that S1 is Q1 and P1, and S2 is Q2 and P2. So to get this size, you just do P2 minus P1, right? And to get B, you just do Q2 minus Q1. You see that? So basically, effectively, A and B become P2 minus P1, and B becomes Q2 minus Q1. So we had C equals A squared plus B squared. We can just plug that in there, right? And we have P1 minus Q1 squared plus Q2 minus, I think I have an error here, right? So this should be P2. Yeah, P2 minus P1. Sorry, I wrote that. All right. Sorry about that. But yeah, so it's P2 minus P1, and then this one is Q2 minus Q1. Do you guys see that? So I'll correct this. And this is basically the Euclidean distance function. Okay. So what's important here is you're going to have points that are represented by these values, P1, Q1, P2, Q2. These are the features basically, like the F1, F2. And then you'll be able to do the calculation of the Euclidean distance. So let me correct that in the whiteboard. I didn't notice I had that error, sorry. Twin beam. Sorry. All right, so let me go to the whiteboard. So this idea can be extended. So I'm going to go over here. This idea can be extended to points that have more features. In this example, we had a two-dimensional thing, right? So we only had P1 and Q1. But you can also have points that have more features, which is P1, P2, P3, dot, Pn. And then this one would be Q1, Q2, Q3, Qn. Right? So the previous one only had two, right? And it tied really well to, like the geometry of it. This one has more, which basically translates into, remember, F1, F2, F3, Fn. It's the exact same idea, okay, in higher dimensional space. And the Euclidean distance function just becomes, for 2 points, it's still 2 points, just in a higher dimensional space. So then the distance between these 2 points, the Euclidean distance, is now square root, right, of P1 minus Q1 squared plus P2 minus Q2 squared. But you can, so basically you're just taking these, right? So P1 Q1, P2 Q2, Pn Qn squared. Do you see that? So you just repeat this. So basically this becomes what you always see like in math operations. If you've seen this, I'm sure at some point. Like I said, I will fix that error I have in my graph. I didn't know I had it. All right. And you've probably seen this equation at some point. So the Pi minus Qi squared. You see that? So this is basically a generalization of that operation. Okay, but it all comes from the Euclidean operation. This is what we will be doing. And the key thing about this is that equation does not care about the takeaway here is that it does not care about the size of the space, whether it's R15, R784, R10,000, because you can simply just do this operation for all the points, right? So you're doing it for all the points, for all the elements of the point, okay? Yeah, and that's it. So going back to the example, I think I messed up something in there. So this is correct. A, P2 minus P1 is that, and then for B is Q2 minus Q1. So this is correct, right? It's this one that should have been P2 minus P1. Okay. So basically this just is literally in 2 dimensions, but we're going to need an equation that works in multiple dimensions. And the generalization is that you can do it as I showed in the whiteboard. like that, basically. So you just, here we don't just have 2 features for the point, we have n features for the points, which translates into this. Got it? Does that make sense? I'll retouch on this on Tuesday. I'll fix that graph. Take a look at it. But yeah. Any questions? Questions? You guys get the idea of how the Euclidean distance generalizes to points that have more features than just 2? Yeah, that's really key, right? And so then that works. And that's basically what we're going to implement in the code when we take a look. So I'll kind of just wrap up with that today. So if we go to the GitHub here. So we are going to have the function of KNN, which is going to be that's what we're going to use to calculate the distances between 2 points. Okay, the Euclidean distance. If you notice, it's the same format, right? You can see where it's coming from. V1 minus V2 squared. And we take the sum of it and the square root. You can see that there. The only thing that's not going to be, it's going to be different is that you probably want to do this with a for loop, but we're not going to do this with a for loop. Instead, we're going to use it through NumPy operations because it's a vector operation, right? So that's the only thing that's going to be. But as I said, I'll start with this on Tuesday. I'll fix up that graph, and then we'll take a look at that. Any questions? No questions? Right. All right. So this is a good stopping point. All right. We won't do any coding today. I'll stay a few minutes if you have any questions. Otherwise, I'll see you Tuesday. We'll pick up with this, and then we'll definitely implement the code of KNN on Tuesday. Yes.
Question, something that I want to show you.
Yeah.
About the Weka homework.
Uh-huh.
So one of the,
Yeah, please.
so one of the data that I found in classification,
Mhm.
The sample, is not even, so it's imbalanced, right?
Mhm.
Both for both species. So in this case, it's like it's a rice species.
Yes.
So from the website, and after when I downloaded it, it was an R file. And once I opened it, I noticed that they're 2 different, they're not the same number of samples. So what I did was, if I do it like this, if I just continue with the model, it's gonna give me an inaccurate result, like you said. So to do that, what I did was to make an equal number, I just removed.
You don't have, let me, yeah, I see
Yeah,
what you're doing.
yeah.
Let me see the number.
Yeah.
So it's 1,630 to 2,800. So that's actually somewhat balanced. That's okay.
Really?
Yeah.
Okay.
My point was, if you had like 1,630 in one and the other one was 35,
I see.
that's gonna be a problem. But here the model might learn.
Okay.
You can drop some, that's perfectly fine, but
yeah.
you don't actually have to, because in real problems, they'll never be 100% even.
Right.
So it's okay to have a little bit.
I see. Okay.
And when I see 1,600 versus 2,100,
Yeah.
they are,
Well, I mean, I just dropped the second species to, and I made it even, so both of them were 1630.
that's fine.
But I mean, yeah, I just,
That's okay
for
too.
more accuracy, I guess, I just did it. I
Just
didn't know that-
discuss it. I mean, it's
Yeah,
an
yeah.
interesting thing to talk
Yeah.
about. Yes, sir.
Yeah, that, not true, right? You know, for the classification.
The NumPy,
No, classification and regression.
the Weka one.
Yeah, the Weka.
Uh-huh, what about it?
How do we transform it to PDF?
You mean from the Jupyter Notebook? I think you can just do print.
I know how to do it from the Weka.
Oh, from Weka. Oh, you can't, just
do we-
generate a report, take screenshots.
Oh, just special.
Yeah, because that's just a GUI thing, so it's
I'm
not,
like, wow.
no, just take screenshots and create a,
Oh, from the NumPy, I know how to export that to PDF.
yeah,
The Weka one.
that's fine. Yeah, for a Weka, just screenshots and create a report that way.
Thank you.
That's fine. Yes, sir.
Just quickly.
Yeah.
Not related to the homework or anything. What are
Yeah.
the prerequisites for this class?
265, why you,
No, because I'm a transfer student, so it was,
okay.
I didn't take no other classes besides last semester was like photography and disaster recovery, but all mine came from Indiana University.
Okay. No, I mean,
So I
if,
was just curious if there's anything I need to brush up on.
Python 265 is supposed to teach you some of the NumPy stuff
Okay,
so that you've done some of the exercises.
okay, yeah, when I took Python at Indiana, there was
No, but yeah, so that's, so 265 is intro to AI.
okay,
And then, but they do teach, they do like NumPy and things like that, so you guys don't see it for the first time here. Knowledge of Python, some programming, I mean,
yeah. It's just,
actually the coding is not that difficult.
Mhm.
What's difficult is the NumPy stuff,
Right.
probably, because we don't do things the traditional way. Yeah.
okay,
But and then the web is just all the students here know about web development and stuff
Yeah.
like that. So I don't know if that's an issue. Huh?
no, I didn't take that over there.
Oh, really?
Yeah.
Okay, yeah, so they take a lot of web stuff, so
Okay,
but it's not that difficult.
no, it's pretty,
And I provide all the code, so you just really have to understand it.
and then manipulate it.
Yeah, exactly.
All right, thank you.
Yeah, take care.